Hi, I'm Nikos, and today I'm joining you from London, where I have been located for the last couple of years working as a software engineer. For the last few years, I have been working for Expedia Group, and I have been involved in different spaces, including web engineering, developer productivity, and more recently, platform and reliability engineering. In this presentation, I will present our journey on scaling chaos engineering across the company as part of our new on-road platform experience. But first, what is chaos engineering? This goes back to Netflix and other companies that defined this space more than 10 years ago. Chaos engineering is the discipline of experimenting to ensure that the impact of failure is mitigated. A critical concept in that area is that of a chaos experiment, which follows this cycle. First, we define our steady state. For instance, our service is healthy based on a set of metrics. We then create a hypothesis. Let's say if we terminate one or more instances of our service, this remains healthy. After that, we inject the failure into the systems and services. And finally, we observe the impact of these failures into the systems. We may find that our alerts did not trigger or that our service level objectives are not met, in which case we proceed to certain actions. And we repeat this cycle until we are confident enough about our systems. Why did we need a solution in that space in our company? Expedia Group is an umbrella of brands, in fact, more than 20 brands in the travel industry. Iconic brands such as Expedia, Hotels.com, and Vrbo. These brands came together as part of a transformation a few years ago, and we worked together with the engineering teams in order to move to a common tech stack. Expedia's platform provides access, as we said, to more than 20 brands and 200 websites in 70 countries. Our platform serves more than 600 billion predictions using AI, and we process more than 70 petabytes of data. This platform provides access to millions of properties, thousands of activities, and hundreds of airlines. To accommodate our new scale, we made the decision to re-architect our systems and to rebuild our platform from scratch. Based on our new architecture, we have more than 35 functional domains, such as cars, flights, or search, and more than 15,000 microservices. The majority of these microservices will be moving to a common runtime compute platform consisting of hundreds of clusters running across a fleet of tens of thousands of nodes. As we want to be as resilient and as reliable as possible to our customers, we operate and run our services in multiple regions in AWS. In addition to this new scale, there was one more reason that triggered the decision to re-architect our systems and rebuild our platform. Over the years, engineering teams at Expedia had a lot of flexibility to use their own tools, their own tech stack. Engineering teams at brand Expedia would use one or more runtime platforms, one or more observability tools, or even service meshes. The same goes for engineering teams at Vrbo and at Hotels.com and the other brands. As part of our journey, we are creating an on-road experience with a common toolkit for our teams. We strongly believe that by having a common platform and scaling tools across a company, we will be able to invest on these tools, invest on integrations, and on providing a seamless experience. This will enable optimizations. It will enable more focus on documentation. It will prevent context switching and specialization in multiple technologies and tools. And in general, it will enable economies of scale. Moving to this common toolkit and platform, as you can understand, is not easy and it takes time. We are not there yet. However, our teams have made great progress and teams are now onboarding to it. The same goes for our chaos engineering tool. We had many tools used across the company. In fact, more than 20 of them. Open source tools, in-house ones, licensed tools. And as you can understand, these tools would integrate with only a few of these platforms and tools, and the return over investment would be very limited. By moving to a single chaos engineering platform, we can now invest on integrations and on providing great developer experience to our engineers. In machine learning, there is this concept of gradient descent where we try to optimize an objective function. In reality, objective functions are not simple, and we may have many local maximum. This concept is similar to providing an on-road experience. If as a company we manage to scale these tools and have a single platform, we will be able to move from local maximum to global maximum. As we mentioned in the previous slides, part of our new on-road platform experience will be a single chaos engineering tool. Our vision was the following. We wanted our engineers to be able to visit our chosen continuous delivery tool, which is Spinnaker, and its user interface, and to be able to run chaos experiments through that user interface without worrying about internal implementation details and abstractions. But first, we needed the building blocks. When we evaluated products in this space, we went back and forth between the usual decisions. Should we buy? Should we invest in open source? Should we build something in-house? We also evaluated the internal tools we had. As we said, we had more than 20 of these tools internally. And we made the decision to use a project that has been open sourced by the Datadog chaos engineering team. The project is called Chaos Controller. It is hosted on github.com. And it is essentially a custom Kubernetes controller, which enables execution of experiments on Kubernetes clusters. The way it works is as follows. There is a contract between the customers and this controller or agent. And this contract defines a chaos experiment. Upon receiving this as an event, the agent spins up the so-called injector pods, which are static pods on Kubernetes, that will inject the failure into the infrastructure. With respect to the supported failure types, we have identified four main categories. This agent supports state disruptions, as it can terminate nodes and containers. It can disrupt resources, including CPU and disk. It can target the network by dropping, corrupting, or even delaying packets, or do wider failures such as impacting an entire availability zone in AWS. It also has support for request level failures, such as manipulating the status code of a gRPC service through a proxy. Providing this agent as it is was not an option for us, for certain reasons, including auditing, compliance, and security requirements that we need to meet as a company, but also due to internal abstractions we have. As you can see in the architecture, our internal customers, who are engineers, can visit our continuous delivery tool, Spinnaker, and the user interface. They provide the cluster's coordinates and the link to their experiment's definition there. And then what you see in the blue shaded region are any customizations we had to do in the Spinnaker components. For example, we have customized the orchestrator so that it includes all the logic we need for the new stages that one can use to execute chaos experiments. Also, we have customized the component that is responsible for the cloud operations so that it enables us to communicate with internal registries, artifactories, and also with our control plane. The way this request flows then is as follows. The users start the experiment through Spinnaker. The request flows through the customizations and the Spinnaker components. It ends up as a custom resource in our control plane and then gets deployed into the worker clusters. After that point, this agent will see this event and it will spin up the injector pods to inject the failure into the infrastructure. And this is how it all looks like in the user interface. On the left, you can see a screenshot of the user interface that our internal customers can use to add this custom stage for executing experiments. As you can see, the customers need to provide a set of parameters. These parameters, we call them a cluster coordinates, and they uniquely identify a cluster. They include parameters such as the PCI region or the cluster name or even the AWS region. The users also provide a link to their experiment definition as this is hosted in Git. In the screenshot on the right, you can see how a finished experiment has progressed over time. The engineers have the option to immediately terminate an experiment, which is very critical. For instance, if something goes wrong. This user interface gives them the option to click on links, such as ones in observability platforms, which are hopefully useful to verify the impact of their experiments. These links are not only useful for our engineers, they are also useful for us as a central team. We need to have a way to troubleshoot this platform. Which leads to the next question: how can we test and debug these platforms? For this, we first rely on a simple architecture that is provided in the open source project. We have a curl pod which talks to an Nginx web server through a Kubernetes service. And like that, we can identify and verify the impact of network failures. We have also created a simple web service that exposes REST endpoints and gRPC services. Using that service, we can, for example, test the impact of DNS failures by attempting to resolve a host name. Even more importantly, we need to make sure we have visibility into this platform's health, which is why we created a set of operational dashboards. These dashboards give us visibility into the health of the different components behind this architecture. We know and we alert on the availability of these components, or even in version discrepancies as we deploy these components into hundreds of clusters. We have also created a different set of dashboards which help us extract statistics. We can use these statistics for decisions such as ones for investing or even for exiting a project. As you can see in the screenshot on the right, we have visibility on the number of experiments that have been running over a certain time period in the clusters, or even a breakdown of experiments per type, per cluster, per AWS region. So far, we talked about the importance of an on-road experience, the need for consolidation, and any operational concerns. However, first and foremost, it is very critical to have a product mindset when building these tools. In addition to our strategy, which is to run programs to promote these tools, we use a set of tactics too. We have created bite-size videos that we promote through newsletters and Slack channels and through our documentation. We also write internal success stories in our documentation and internal blog. In fact, we encourage our engineers to write these stories whenever they execute experiments. Sometimes we publish blog posts in our public Medium account too, which we hope are useful for the wider engineering community, not just for our engineers. More recently, we have been experimenting with this idea of architecture-driven game days, where we work with the domain teams. We go together through their domain's architecture. We then focus on certain parts of this architecture, identify failure points, inject failures, and finally observe the impact. This aims to better prepare these teams for incidents. The chaos engineering platform is just one of the tools that our teams have been working on. How do we make sure then that we close the feedback loop between people, processes, and tools? This is where the Reliability Hub comes into play. The goal of this hub is twofold. First, it aims to provide a set of practical guidelines to our engineers in order to be able to design highly available and reliable systems. It also aims to provide a summary of the different products which are available internally in that space. How do we make these best practices practical? Here we rely on two entry points. One being the runtime platform where many of these are implemented, and the second one being the language tools, the various SDKs, the templates we have internally that our engineering teams are using to bootstrap new services. For example, we encourage our teams to enable autoscaling in their applications. Autoscaling already comes out of the box through the horizontal pod autoscaler in our new runtime compute platform. That said, our engineers may need to tweak the configurations. A similar example, we encourage the teams to have circuit breaking whenever their services are calling dependencies. Circuit breaking with sensible defaults again comes out of the box in the SDKs and the templates we have internally. The question then is, where does chaos engineering come into play here? The majority of these best practices can in fact be verified through chaos experiments. For instance, one can verify the configurations of a circuit breaker by executing network failures. It might seem counterintuitive that we created this reliability hub only at the end. It is. However, sometimes in order to see the big picture, you need to have the building blocks in place. What are the key takeaways of this presentation? First one, invest in proactive reliability and don't have reactive strategies only. This can be achieved by using tools or even by running chaos experiments into your systems and services, which will essentially better prepare your engineering teams for incidents. Consolidate tooling and, if possible, create this on-road experience with a common toolkit used across the company. And make sure that these tools integrate seamlessly with each other to provide a nice experience to your engineers. Focus on adoption, and the most critical part, never forget your customers. Make sure that you get feedback early and constantly from them, and that you address that feedback in order to improve the developer experience of these tools. It is only then that you will have products which are used by and loved by your customers. We have published a blog post about this work a couple of months back. This has evolved a lot as a platform, but we hope it is still an interesting read. Thank you very much.